This is Dr. Ali Mugabe, and we'd like to cover union bound on probability of error. So when do we do a mistake or error? For example, if we send a message M1, this point, if we send this signal, this one, but for a reason or other, because of noise or what have you, we are receiving a point in this gray region. All these points are going to be decoded in the wrong way. So to define this region, we need to define our double integration. We have double integration because we have two bases. So anything beyond these two lines is going to result in error. So we need to define these two lines. The numerical computation of the integral of the average of probability of error of the symbol that we transmit is sometimes difficult. So in this example, maybe we can easily distinguish the region to some extent, but it's not always possible to do that. And sometimes it is doable, but it's not practical. So to avoid going into mathematical complexity, we use bounds. So instead of giving you the exact probability of error, I'll give you a bound on the error of probability of error. So to predict the signal to noise ratio required to maintain a given probability of error, we need to use a bound. So if we are beyond that signal to noise ratio, we will guarantee at least that we're getting the required communication. So why do we call it the union bound? We know what the bound is. Now we need to understand what the union bound is. Let's define AIK to be the event that we transmit SK, which is the second subscript, but instead we're sending, I, the first subscript, but instead we receive SK. So SI was transmitted, but SK was received. So it's like this is the probability of comparing just two symbols at a time. We can have A12, A13, and A14. All of these are conditioned on the fact that we have transmitted I, or 1 in this example. Now, if we consider all of them, I sent S1, I get S4, I sent S3, and I get it's closer to S2. If we consider all of them, then we get the union. If we sum all these probabilities, then we're going to get a bound on the probability of error. And we'll see in the next slide why this is not exact. Why is this a bound? Because what happened is that we are taking pair at a time. This is this bound. As you can see, we have a union here. It's called the union bound. Now let me explain why this is not exact answer and why we have a bound. If you look at the same example here, what we did in the beginning, we considered transmitting S1, and the shaded region is indicate that we have an error. So the first probability of A2 is in fact cover anything in this region, because comparing S1 and S2, we can draw a line connecting them, and then we get a bisector, we get a point in the middle, and we draw a perpendicular line. So if you want to distinguish the region of decision between 2 points, symbols, you draw a line connecting them, and then you draw a vertical or perpendicular line in the middle. So this region is the region that covers A12. And then now for A13, we have this region, anything in the lower part. And then finally we have A14. So you can see that if you concatenate all of these three together, we'll have some overlapped region, something that we have accounted for more than once. And this is why this part in the middle and the beginning and the lower part will be counted twice. So in fact, we can even drop this and still get a union bound, which is maybe tighter, but still we have a probability of error because things would overlap. Now, the union bound on the probability of error. There is a difference, clear difference, as we have seen, between what we want, the probability of making a wrong decision, and or the probability of picking S2 when S1 was transmitted, because in this case we consider all possible symbols, but here we are only looking at the pairwise error probability. So PM hat equal to MK given MI indicates that X lies closer to SK compared to any other vector if SI was sent. However, if you look at A's just depend on two signal vectors, and we are looking at what we call the pairwise. We're looking at the pairwise error probability, okay, which is given by the following. The pairwise error probability, it is the probability that a receiver mistakes SK for SI, assuming that the system uses only pairs of signals. Other signals, they don't exist. So we expect that the true probability of error will be less than the pairwise error probability which we use in the union bound. On the diagram, on the constellation diagram, we can look at the probability of S1 SIK given that MI was sent. And if we assume additive wide Gaussian noise channel, okay, basically if you compare, for example, S2 with S3, then this is the decision between the two relies on the x-axis. So we are sending a center power, the average power, if you are sending S2. But due to the noise, what you are going to receive is not this exact point. It could be here, amplitude, or it could be lower, it could be even negative. So this is the Gaussian PDF that represent the coordinate on the y-axis. So when are we going to go? When are we going to commit an error? If we cover this region. So yeah, although this is shifted, but we can think of this as this entire thing is the distance between the two, and this is the middle region. So this is DIK divided by 2. So we're integrating. We're, of course, because this is symmetric, you can take this, you can take that part anyhow. So this is from the middle to this point, we have DIK over 2, and then of course we integrate up to infinity. This is the Gaussian PDF, and the shape of the exact Gaussian, it depends on the amount of noise. So if we have more noise, then things would look like this. If we have less noise, then the tail becomes smaller, and then we get less probability of error. Remember that the area is always equal to 1. Okay? So similarly, if you want to find in the vertical direction, you can think of a one-dimensional problem, and you can find the distance and integrate in the same way. Recall that the integration of Gaussian to find the CDF of Gaussian, we don't have a closed form expression, so we can use the Q function, the error function complementary, or the error function, any of the tabulated functions. And for example, if you compare these two together, if you want to use the error function complementary, ARFC, which is also available in MATLAB, we can use also the Q function. They are related to each other. There is a difference between the limits and some constant multipliers. So if you compare these two together, you can assume that Z equals to V over square root of N. So now if you square Z, you get the same expression here. And then you can find dz equal to dz equal to dv by square root of n naught. And of course, this is going to cancel out, and this way you get just square root of 2. With a little bit of simplification, math, we get the expression at the bottom. So we go from here to here by the following expression. Remember that there is a scaling factor of 2, which is missing here, so that we end up with this expression. This gives you the probability of error for mistaking. This is the pairwise probability of error. It comes from the Gaussian, because we assumed Gaussian. Now, if you want to go for wireless channels, then you need to change your PDF. Instead of saying Gaussian, it could be Rayleigh or whatever. You put the right PDF, and then you get the right answer. So when we get at the Euler bound, we need to consider both of them. So I have the summation, okay, for all possible values of k does not equal to I have to consider all possible symbols, and then I substitute into the limit k equal I up to m, where ki does not equal to I itself. And of course, every time we need to find what's the right distance between them, okay, because the distance will determine the probability of error also. So the average symbol error rate over all possible values of m, if you want to consider all of them, this is only for one symbol. You scale every symbol its probability with its probability of transmission, and you add them all up, and you will get the probability. So this is why you have double summation. The first summation is for one symbol compared with other symbols, and then we have to extend this to all other probabilities. Of course, in the case that it's symmetric, we can simplify things. We can get only the expression here. There is no need for the second summation. What comes next, we can also simplify. We can get different forms for simplification for the probability of error expressions. So the pairwise error probability is given by the following bound. This is the union bound after looking at all possibilities. In case of circular symmetry, which means all symbols are the same, like in the example of the Q of 4 PSK, QPSK here, then we can, one of the summation will be dropped because finding the probability of R1 is just like the others, and also we can assume that all of them are equally probably transmitted. So this is a QPSK. We call it Q because we have quad, we have 4, and phase shift keying stand for PSK. For this kind of constellation, how do you reduce the probability of error? You can always increase D or decrease N naught. This is usually not in our control, and this requires power transmission, which is costly, so we have to trade off things. In the following example, we consider the example of QAM, quadrangular amplitude relation, especially if we have large number of constellation points and capital M is relatively large. So what do we do? Instead of measuring all the distances, we can do that, of course, but to get a nice form expression, we can simplify things. We would assume that what matters really is the closest distance. So it's true that you can mistaking this with that, and then this with that, or even this with that, whatever. All right, but what is highest, the one that will have higher probability is the closest distance. So we're going to characterize the bound by, we call it the minimum distance bound. And instead of finding all the distances, we will assume that the minimum distance of the signal, dmin, it's the smallest Euclidean distance. So dmin, it's the minimum of all possible di's where I does not equal to k, of course, because if you compare a point to itself, you'll get a zero distance. If that's true, if you want to go with the minimum distance bound, instead of summing for all possibilities, we know that if we, you know that error function is a decreasing function. So decreasing dmin means it's going to increase. So this part is higher value than this. Although dmin is smaller than dik, but the error function itself is decreasing function. So decreasing the argument will increase the function. And this is why we're saying this is greater than or equal. Now we can go back to our bound. Instead of the summation, we'll assume that all of them have the worst case, and then it's half times the error function. If you recall, we have this comes from the original expression, and then we're going to assume that they are all the same, and that will give you m minus 1. So all possible cases, we have m minus 1 of these when we sum. Minus 1 because, of course, we exclude the transmission, the symbol that was transmitted, because that will not cause an error. The example shown on the side here is the 16 QAM. This is not ASK, this is not amplitude, this is not phase, because they are different in both amplitude and phase. This is 16 QAM, 16 because we have 4 by 4, 16 different points, constellation diagram. This is an example where we can use d minimum to simplify things and instead of doing the probability of error for all. We can go further and simplify the expressions by using exponential approximation. So if you don't have the calculator or the device to find error function complementary or the tables, mathematicians give you another bound. This exponential is always going to be greater, so we can, even if you like, we can use this bound, and then things will be written in terms of exponential. This will prove to be handy if we have exam or so. Instead of giving you the error function tables and so on, we can use the exponential approximation. Of course, that will also give you another bound. We see from the above that the error probability decreases exponentially as a square of the minimum distance. As you get the points to be away from each other, you expect to get less error, and that's square because the energy is related to the square of the distance. The second note I'd like you to keep in your mind here is that the average probability of simple error is important for noise performance of digital systems. Another important measure is what we call the bit error rate, or average probability of bit error. We want the average probability of bit error, not the symbol rate. Bit error rate versus symbol error rate, or symbol error probability. In the following, we look at the relation between the bit error and the symbol error rate. In fact, there is no unique relation between them, but we can do some approximations. For example, if we use gray coding, then with gray coding, we try to assign the symbols such that adjacent symbols are different by the minimum number of bits. For example, if you go from here to here, then we have only one bit that's not correct. If we go from here to here, we have only one bit that's different. So although every symbol has 3 bits, but we get 1/3 of them in error. So we can say now that at worst, you get all bits in error, and in that case, the probability of symbol error equal to the bit error rate. Okay, at best, if you use gray coding, then the probability of error, if you can, then it's always going to be divided by log m base 2. For example, here we have m equal to 8. It's going to be divided by 3. So because out of the 3, only 1 bit is error sign. This is just a bound. Because when we do an error, it's also possible that we do a mistake, and not just with the adjacent one. We can do the mistakes, and we get shifted to another symbol. All of them has to be accounted for. In the second case, we'll consider an example where capital M equal to 2 raised to 4k, where k is the number of bits, and of course m is the number of symbols. If we assume that all symbols errors are equally probable, you can do a mistake by going anywhere, and they are all equal probable, then the probability of error, okay, for all of them is going to be divided by all possibilities. This is the probability of making error. You divide by m minus 1 because we have different symbols, and in any one of the symbols you're going to get m divided by 2, the number of bits, because we have m divided by 2. Out of that, m over 2, the average. We assume that in the average we have half of the bit is wrong, so we can get the following expression. Now in terms of m, this is the expression. In terms of k, here is the expression. As you take the limit for large values of m, this is going to tend out to be half. So half of the bits are in error, of course, under this assumption, which is of course a bad assumption. I mean, it's usually much better than this. Oh, the last comment here is that bit errors are not independent. For example, if you have a sequence of bits, the probability that this is an error is not independent of this. So usually they are related, as we mentioned here. For example, if this is an error, there is high probability that this is not an error, because we arrange them in a way that make them dependent. So the probability that the ith and the jth bits are an error does not equal to the product. It's not equal to the multiplication. It's not equal to bit error rate squared, because they are dependent. With this, we get you an idea about how to calculate the bit error probability, the symbol error probability, and the union bound. We'll use this background to develop our understanding, and we'll see how to extend this also into more complicated examples and different distributions other than Gaussian. Thank you for being good listeners, and see you in coming videos.